Welcome everyone to the One World ABC seminar. Today's speakers is from Queensland University of Technology in Brisbane, Australia. David Warren is a lecturer in, actually I was about to say lecturer in statistics, but you are a lecturer in statistical inference for complex models. So this is a pretty cool title.
That's the full title, yeah.
That's the full title.
Yep.
Yes. And you're going to talk about a very interesting topic, multi-fidelity, multi-level Monte Carlo for ABC. We had a chat before a few minutes ago, and yes, I will invite you to check his publication, his webpage, because he has a large number of cool papers on several broad topics of theoretical, methodological, and applied interest. So, as I said, we're recording this talk. Feel free to everyone to write in the chat your question. And David, thanks so much for agreeing to be with us. And that's your floor now.
Thanks a lot for the introduction, and thanks everyone for coming along to this talk. It's been a real pleasure to be invited to talk about this research. So. Yeah, I mean, I'll be talking about a topic that brings a few things together. This idea of multi-fidelity, multi-level Monte Carlo for approximate Bayesian computation. Before I get started, again, thanks for the invite and for everyone attending. I would like to acknowledge my collaborators in this work. So this is very much a joint effort. What I'm talking about today. So Tom Prescott, who he was at Oxford and now he's at the Turing Institute. Ruth Baker, who many of you will know at Oxford, and also Matthew Simpson, who many of you will also know at QUT. So Ruth and Matt were both my PhD supervisors, and then I sort of connected with Tom towards the end of my PhD when I started seeing him work on multi-level approximate Bayesian, multi-fidelity, sorry, approximate Bayesian computation. I should also acknowledge some funding. So this work has been partly funded by the Australian Mathematical Society through a Liftoff Fellowship given to ECRs in Australia. Then also the Centre for Data Science at QUT, which I'm a member of. And then also it's finished up now, but the ASEMS, which is the Australian Research Council Centre of Excellence in Maths and Stats. So these three sources have contributed a lot of funding to my time and other computational resources, etc. Okay, so I don't think I need to motivate the work too much to this audience. Stochastic processes are pretty important, and you know, a lot of things, and particularly the life sciences, depend on some sort of stochastic process. And in particular, the things I'm interested in modeling and working with are stochastic processes of biological systems, biochemical systems. And so this is the sort of framework that we're dealing with. So we have a vector of copy numbers for n chemical species, and they interact via m reactions. And so we have these sorts of this array of chemical equations. And these stoichiometries, these basically say how many product molecules you need, how many reactant molecules you need paired together to make a particular product. Right, so it's just chemical equations, like from high school. So the K sub j, these are the rate parameters. So how frequently these reactions occur, and then you have this state change, which is taken by the difference of the stoichiometries, and taking the particular row for that matrix. As an example, we have a very simple system of so-called Michaelis-Menten enzyme kinetics. It's a very simple system where we have an enzyme binds to some sort of substrate to produce a complex, and then that, some sort of catalyzes some sort of reaction to produce a product. And so you have this sort of the enzyme substrate bind, and then they can break down again, or it can produce this product. And so this is the sort of system that we would get. We'd have these three reactions. These are the stoichiometry, the update vectors that we would be using for each reaction event. And then we have these propensity functions. I dropped an equal sign there by mistake. That was good. So our first reaction here is what's called a second order reaction. So we have a product of the two species, S and E, and then the other two of these first order reactions. So we can use these to generate a continuous time Markov, continuous time discrete state Markov process. Okay, and here's just an example, a few realizations of this particular process. From a inference perspective, these things can be quite challenging because firstly, we observe it discretely. So we don't observe all the reaction events, even though it's a continuous time process, we're observing it discretely. But also our observation process, not only could it be noisy, but also we often don't have the full state. So you might only be able to observe a particular protein that's been tagged with some fluorescent, like green fluorescent protein or something like that. And then we may not be able to distinguish, say, individual, say, monomers versus dimers and things like that. So it can be challenging to observe the full state. We rarely have it. So our parameters we want to infer is this theta from some parameter space, capital theta. And we often don't know these. We want to estimate them or quantify uncertainty around them. They could be the reaction rate parameters, but they could be things like initial conditions and other parameters from the model. And from a Bayesian perspective, we're looking at some expectation of a function of that parameter vector with respect to the posterior. Okay, so this is not new to anyone. We generally never have the normalizing constant, so we rely upon things like SMC or MCMC. But also in this case, because of the partial observations, we end up with this quite challenging looking likelihood function, which for all intents and purposes is intractable because it depends on the chemical master equation. And then we have to integrate out all the latent states to be able to get our observations. Now, I know there's a lot of techniques to deal with this particular type of problem, but more generally, this can be extended to spatial systems as well, and they get really nasty really quickly. So, for all intents and purposes, we have an intractable likelihood, and so we rely upon this likelihood free, and of course we have the common approaches like ABC, which is what I'm focusing on. But we also have pseudo-marginal and synthetic likelihood that both could be applicable to these types of systems. For ABC, you know that we have this discrepancy metric and some discrepancy threshold. We generate simulations from our model for different thetas, and we can get this sort of probability that we're within some sort of threshold of our observations to get this approximate posterior, and characterized, simply by rejection sampling, sample from the prior, simulate our model, and then accept it or reject it based on how close it is to the data. So that's not new to anyone. So we need simulation. So for biochemical networks, we can do exact simulation with Gillespie's method listed here, which I won't go through the details of that because I think a lot of people probably know it pretty well. But ultimately, we are able to generate exact sample paths of a biochemical network. But to use this for ABC, even when you're using things like SMC or MCMC, it can be very expensive because firstly the cost of one of these simulations depends on how I guess the average reaction rate. So that's enhanced by the number of molecules in the system, but also the rate parameters. So both of these things control how many reactions are occurring over a time window, and it can get very expensive very quickly. And if you're wanting to take your ABC down to a very small epsilon, you see that very few sample paths, even if you have the right parameter value, are actually going to hit the area of your data. So rejection rate is high and each simulation is expensive. So we want to avoid doing Gillespie's method if possible. So we can look at approximate simulation where we have some constant tau, and we look at this tau leaping approach, which is basically assuming that over this period tau, the propensities aren't changing too much. So in that case, you can come up with something like this, where we use Python process, and we can get this this fixed compute time independent of the number of the parameter values. So that's good. We have something a little bit more deterministic in the runtime, and depending on tau, it could be quite computationally cheap. But now we have to worry about the bias in the simulation. And furthermore, we don't really have a good view of how this bias in the simulation propagates through the inference problem. So these are the sorts of things we want to be able to deal with. And that's the focus of I guess, the multi-fidelity work. So I'm first going to talk about a paper which is a little bit about multi-fidelity likelihood-free inference that we sort of build upon a special case of this for the multi-level thing. So I'm just going to go through this a little bit just to give you a feel for the generality of what we're trying to do here. So the setting that we're looking at, we have some observations from some data space Y and a likelihood that's intractable. So let's say we simulate a block of K simulations. So we have a bunch of simulations from our likelihood for a particular value of theta. And we're going to define this approximate likelihood function, which is an integral over all possible K length blocks that we could possibly do. And I sort of abuse notation a bit here. So this is the probability of one of these blocks given a theta. So it's a product of this one. And we integrate over Y to give us this expectation in omega, which is this, what we call likelihood-free weighting function. Now, this is not a typo. It's a little bit, it might seem a little bit odd at first. So we have the parameter space and the data space. We map that to a value on the real in the reals. So this omega, we're actually allowing to also be negative, which would seem odd at first, but there's a reason why we do that. From this, we can define this likelihood-free posterior, which is proportional to this approximate likelihood times prior. And it turns out that we can recover the, I guess, more standard likelihood-free approaches with special cases of this weighting function. So for example, for approximate Bayesian computation, we would have this summation for the accept-reject conditions for the K simulations. We can also do a pseudo-marginal sort of case where we decompose the likelihood like I showed on that first slide, and we simulate the underlying process and the noise process and work out the probability of the data on that. And of course, this would work best with particle filters and MCMC and things like that. So, but the point is we can represent pseudo-marginal within this system as well. And then also Bayesian synthetic likelihood. Our weight in this case is the Gaussian PDF with the mean and covariances computed from the data. Okay. So with that in mind, we can now start to think about a broader class of likelihood-free methods where we can define one of these weighting functions and think about what sort of properties it might have. And so we're going to look at computing an expectation with respect to one of these approximate posteriors. So that could represent ABC, pseudo-marginal, Bayesian synthetic likelihood. I guess the key thing to emphasize here is that we're not necessarily saying that for any choice of omega, that this is going to be a good approximation, right? So if you imagine ABC with a very, very large acceptance threshold, it's not going to be a good approximation for the posterior. And similarly, pseudo-marginal with very few particles and Bayesian synthetic likelihood depends on the problem altogether. So at the moment, though, we say we have this approximation and we're looking at an expectation with respect to that. So within an importance sampling framework, we can define this likelihood-free importance sampling and come up with this estimator here. And it turns out that when you look through all of this, we can say that f hat omega is a consistent estimator for this expectation. Okay, so that's a fairly standard result from importance sampling, but this holds for whatever omega you choose. Whether it's a good approximation for the posterior is a different question. Okay. So this allows us to play with this a little bit and extend it to this idea of multi-fidelity likelihood-free. And so here we say that we've got some sort of low fidelity simulator, but it's cheap. So it could be tau leap, it could be other things, different models. So we're still keeping this quite general. And I'm denoting the simulator by this tilde, the p tilde. So anything with a tilde is from the approximate model or the low fidelity model. And we're going to say that we're going to simulate a block of k low fidelity simulators and then m batches of k high fidelity simulators. And the m we'll talk about in a little bit. But if we go ahead and do this, we end up with this, this set script Z that has our approximate batch and a whole bunch of exact or high fidelity batches. And that's defining them there. So we have the simulations from the approximate, simulations from the high fidelity model. And if we choose m to be a random integer, random non-negative integer, with this sort of condition, so we have some sort of expectation that's conditional on the parameter value and the approximate simulations. That gives us the mean for this non-negative integer mu. And our main condition is we need this to be greater than 0. So provided we have this, we can define this multi-fidelity likelihood-free weighting. And when you go through this, we can say that this is also a consistent estimator, but it's a consistent estimator for the high fidelity expectation. So this is what we're sort of thinking about now. So we've generalized the idea of likelihood-free. We've been able to apply it to this idea of likelihood, multi-fidelity likelihood-free. And that allows us to now create a whole family of these multi-fidelity methods. And the example I'm going to show is this idea of multi-fidelity rejection sampling. So this is a special case and it was developed originally by Tom Prescott and Ruth Baker in 2020. So this was a special case, and we went to the general case. And so in this case, we have K is 1, and M is just a Bernoulli random variable. And we have the expectation of that Bernoulli random variable is given by this equation here. So essentially, it comes down to a probability of, well, it's got one condition when you have a rejection or an acceptance, sorry, in this case, when you have an acceptance of an approximate simulation, it evaluates to N1 or eta 1. And then when you reject the approximate simulation, it has an expectation of eta 2. And then our weighting function is just ABC weighting functions, K equal to 1, okay? And we just have the approximate model here, low fidelity, and then the high fidelity model here. And if we set the proposal distribution to be the prior, then we end up with this for the multi-fidelity weights. And so really what this is saying is that if when we calculate, so we basically simulate our low fidelity model, we accept or reject it, and based on whether we accept or reject it, we have a continuation probability. So M will be 1 with some probability eta 1 or eta 2, and that will tell us whether we evaluate this part or not. If M is 0, then we don't have to simulate the high fidelity model. And so to get this thing all sort of working well, we want to be able to optimize these continuation probabilities. And so ultimately, we're going to minimize this function here, which is sort of balancing the, I guess, it's really minimizing this is sort of equivalent to maximizing the expected sample size. Okay. And so we want to find the eta 1, eta 2 that minimize this function. And it turns out that there is an analytical solution to this, but it requires knowing the receiver operating characteristics, and we don't often have that a priori. So it's not easy to use directly. So what we instead do is we just sort of start simulating with, say, n with eta 1 and eta 2 being, say, equal to 1 initially. And we update this as we go using an exponentiated gradient descent. We have our gradient for this function we're trying to optimize, and it's written in terms of the following parameters. So we have the expected cost of the low fidelity model, the expected cost in the case where we have positive, so we accepted the approximate model, or negative when we rejected the approximate model, the expected cost when we continue. And then we have the ROC parameters, so true positive rate, false positive, false negative rate. So we still need these as inputs, but these can now be estimated as we go. And by doing the gradient descent, it sort of stabilizes things so we don't end up in a silly ridiculous spot early on. And it allows us to sort of gradually move towards the true optimum as we progress. And so as we progress, we update these estimates, and then we can adjust we can adjust to a new value for eta 1, eta 2. As we run, it just continues to adapt. Okay. So that's all the, I guess, the fundamental stuff in the first place. The idea with the multi-fidelity work, I'll just go back again. One of the challenges here is that it's still based on a particular likelihood-free approximation that you want to deal with. So, for example, if you were using ABC, or for example, ABC rejection, even if you were using SMC, you've still got some sort of target epsilon that's your sort of fundamental bias in the system. Okay, so we want to be able to also deal with that. Because otherwise, if your rejection rate is still very, very high, even if you have, even if you're often simulating the low fidelity ones, it can still mean that you're still waiting a very long time. So we want to be able to come up with another way of pushing epsilon smaller. And to do that, we look at multi-level Monte Carlo. Okay, so this is another bit of work that's sort of done at the same time as the previous section. And so here we're applying multi-level Monte Carlo to the multi-fidelity ABC example that I showed before. So I'm not assuming that multi-level Monte Carlo is a topic everyone is strongly familiar with. So I'll go over that a little bit. So if we have some sort of stochastic process that we can simulate exactly, and a sequence of approximations, and we want this sequence to be such that the bias decreases, but the cost might increase as L, so this is the level, increases. So that could be something like tau leap. But you know, of course, it's also important how the bias decreases and the cost increases. But yeah, we have this sequence, and then we can expand expectation of say some function of the n time of the random variable x. We can expand using this telescoping summation, where we might be able to, we can't always do this, but we have this final sort of de-biasing correction. But then we have this sequence of L bias corrections where we're correcting from level L minus 1 to level L. And so ultimately, when you collapse this all down, you end up with something that's the same as this one. But why this ends up being a good idea is that sometimes, well, quite often, particularly for things like biochemical networks or stochastic differential equations, you can couple pairs from both ZTL and ZTL minus 1. And you can do that in a way so that the estimator for the difference is unbiased. And so provided you can do that, then we get this variance reduction because this will be a lower variance estimator. Sorry, I should have also said that by introducing this coupling, you can come up with a variance reduction, and that overall improves the convergence rate and mean square for a direct Monte Carlo estimator. And this is an example for a chemical reaction network where we have mean squared error in the x-axis and compute time in the y-axis. So here we have our Gillespie method in blue, computing the expectation of, I think it's the B molecules at time 100. Then we have the equivalent direct Monte Carlo if we're using tau leap. And you can see that because of the additional bias, gradually we're eventually going to reach a point where it's not worth doing tau leap anymore. By applying multi-level to the equivalent tau leap, we can sort of get this improved convergence rate. Now, this is without the final de-biasing correction. So if we included that as well, we could get a further increase and we actually improve the overall rate over the direct Monte Carlo. That's the rationale for multi-level. There's a few techniques that can be applied to use this idea for inference. So for example, we have an example with ABC rejection, which I did during my PhD, and then also this nice example of ABC SMC written by AJ Jazra and collaborators. And that allows you to look at this telescoping sum where theta L now is an ABC sample. So we've got a sequence now of thresholds. And so the idea is that we want to be able to apply this variance reduction idea to this expectation. If we apply it directly, direct Monte Carlo with ABC rejection and Gillespie for the underlying simulator, we end up with a telescoping sum like this. The challenge here is in the coupling step. So you notice a little tilde here. That's because when you're looking at the rejection sampler, this ends up being a slightly approximate coupling. So we do introduce a little bit of bias here. Okay, I'll talk through roughly what we do. And so while we're estimating this, this expectation with respect to the terminal level capital L, we also, along the side, we also estimate the marginal CDFs. And we do this in a continuous way. So we actually fit smoothing splines and things. So we get a sort of function for the marginal CDFs at each level. So we do a bit of smoothing around that indicator function. And we also have to do an adjustment for monotonicity, because when you're applying the telescoping sum, a bit like the negative weights in the multi-fidelity case, you can have cases where your CDF ends up having these little wiggles in it. So you can adjust for that without affecting the overall bias. And so we end up with, at level L, we already have the set of approximate marginal CDS for L minus 1 as we've been accumulating this thing. And so then when we sample from epsilon L, we then do another CDF estimate there. And then we map this back to the previous level using inverse integral transforms. Now, of course, this is going to introduce bias if the correlation structure between the two levels changes dramatically. Okay, so there's an implicit assumption here that there could be some change as you transition through the epsilons, but the change isn't crazy. So if things were truly independent and the correlation structure was the same, then this would be an exact coupling. Okay. So this is now bringing everything together. So we have a method for multi-level Monte Carlo for an ABC rejection sampler. What we can do now is replace our original direct Monte Carlo with a multi-fidelity ABC rejection scheme. So that gives us a telescoping sum, or an estimator that looks like this. So it's based on telescoping sum, but here we have multi-fidelity Monte Carlo estimates here. And here, so all these theta L's are all going to be drawn from the prior in each case, because the weight can be 0. And so that's when things get rejected in both cases. But we only have to do this coupling update when we have a non-zero one. So the majority of them are, and if it's 0, it means we only really simulated the exact model, or the approximate model most of the time. So this is all the same as before. We have a sequence of these Bernoulli random variables, and we have a separate mean that we've got a tune at each level. It takes the same form as before. So we additionally couple the low fidelity and high fidelity simulations. So in this case, our low fidelity simulator, because we're dealing with biochemical networks, this is a tau leaping scheme. And we modify this a little bit in that we track the the Poisson rates as we go, and we also store the Poisson random variables. So afterward, after we compute a realization of the tau leaping method, we end up with, I guess, a partial unit rate Poisson process that we can then complete in the high fidelity simulation to form a proper unit rate Poisson process that is, I guess, coupled to that original approximation. So what that means is we can take these parameters from, or these rates and random variables from the tau leap simulation. We can then create an equivalent full unit rate Poisson process. We'll have M of these for each reaction channel, and then we can pass that into another simulator like modified next reaction or similarly equal SB, but that allows us to generate a high fidelity exact simulation that's been coupled to that underlying tau leap simulation, rather than the reverse. Like quite often you end up going the other way. You start off with the high fidelity and you go to the approximation. In this case, we can go from the approximation to the high fidelity. Once we have that, we can use our adaptive scheme from the previous work to optimize this function. So again, maximizing the ESS at each level. So choosing these continuation probabilities at each level, we adapt them as we go. Once we've done that for some trial simulations for a set of different thresholds, and we decide the number of thresholds this way. So we have this geometric sequence from the original epsilon1 to epsilon L, and based on our sort of experiments, I guess, we choose this to be roughly between 1.5 and 2.5, and that's mostly to sort of control that that change in the correlation structure from that approximate coupling. I know for some multi-level Monte Carlo schemes, the optimal L is something like, the optimal M is something like 4. But in this case, if we took big jumps like that, then you could see, big changes in that structure. So this has been working quite well for all the systems that we've been using, but you do need to investigate it. Once we've got the number of levels, we've got this adaptive scheme, we can then derive the optimal scaling for the multi-level Monte Carlo. So that's our sequence of samples at each level. This N sub L sequence will be much larger than the direct Monte Carlo version because of the nature of the multi-fidelity approach. You end up with the total number of samples is much higher, but a lot of them will be the low fidelity model. So that's a lot of them won't simulate the high fidelity at all. Once we've done all of this,
sorry, David, I'm not sure if you commented on this in previous slides. What is that CL in the first equation?
Oh, sorry, I should have spoken about that here. So I skimmed over this equation. So these are the weights. This part's all fine. This is the expected cost at that level given that theta. So that's the expected cost of computing the one of the multi-fidelity weights. So that's over all possible. So whether you continue to a high fidelity or not, it's the expectation over all of them, the average runtime for the weight.
It's something you estimate from previous runs, I suppose.
Yes, so that's why we use this adaptive scheme. So as we're sampling, and multi-level requires some trial samples anyway, so we sort of use these two things together. So for each of our correction steps, we do, I guess you call it some burn-in simulations, where we get an initial adapted set of continuation probabilities. Then that gives us initial variances and costs for each level and then we can come up with this scaling. We need the number of levels already. So we have our threshold sequence. So we do need that a priori. Once we have that, we can do the adapting and the optimal sample size at the same time. And then we do the full telescoping sum.
Thanks.
So the burn-in will be much, much smaller than NL. So we have, let's say, some ML, which is our number of trials. They'll be smaller. So the challenge, and this is the thing that we still need to work on, is appropriately choosing the tau Ls. So from the perspective of the properties of the multi-fidelity method, any tau L will still result in a consistent estimator. But there are obviously choices. For each level, there could be a better choice than for other levels. And it's not necessarily the case that some sort of geometric sequence. So that's requires a little bit of exploration. And in our case, we've been using a constant tau through all the levels. And we've just been experimenting with that number a bit. So now that I'm pretty much done with all the main work, I'm just going to talk quickly through some examples. So we have a nice gene regulatory network through a priscillator model as these, nice stochastic oscillations. It's a nice example, I think, for ABC. And we're going to compute an expectation of the mean for some of these parameters, basically. And so this is can be quite a challenging problem for ABC approaches. And these are some examples of the cost of our multi-level multi-fidelity estimator versus the variance of the estimator for different thresholds of epsilon. And we're comparing this against the ABC rejection scheme, the direct multi-fidelity scheme, direct multi-level scheme, and then our multi-fidelity multi-level scheme. And the parameters we're using for L and tau are there, and the gamma here is an estimate of the convergence rates that we've got. And so we see with both that we get an improvement from any of the methods, but you see that we sort of get the compound effect of improved convergence rate and reducing the overall cost with the multi-fidelity scheme. And if you look here, this is on the order of 2 orders of magnitude here, which is really cool. I mean, this is still rejection sampling, mind you, but the methods I think they can be applied to other things. So this is proof of concept. Another example, which is quite challenging, this 2-step MapK process. So basically, it's a chain of Michaelis-Menten reactions. We have 12 parameters. This is an example of some realizations. In this case, we're only observing the so-called phosphorylized proteins, and the rest of it is all latent. So a lot of this there'll be identifiability issues here for sure, which causes challenges for a lot of other samplers. But we can go ahead, we can apply rejection sampling in our other techniques, and same sort of story. Yeah, really nice speed ups for both. Multi-level by itself performs quite well here as well. So that's really what I have to say. I'm going to wrap it up with, I guess, some future thinking. So I've mentioned the limitation here is rejection sampling. So we want to be able to look at other schemes. I think by having this generalized likelihood-free approach, we can start to play with this quite a lot. So we can apply this sequentially. You have to be a bit careful because the weights can be negative. And Tom can talk a lot more about that than I can. But having this general scheme means you could potentially have mixtures with the multi-fidelity that are not just based on different simulators. They could be based on different likelihood-free schemes. You could have your high fidelity could be pseudo-marginal and your low fidelity is some ABC thing, or Bayesian synthetic likelihood, you can potentially mix these things together. Multi-level also has examples of being applied to SMC and MCMC. So I think that given all of this, there is an approach where we could look at multi-level for either sequential likelihood-free importance sampling or potentially other samplers. For our particular example here, our implementation, there's still some work that could be done. So one of the challenges here with the multi-level is having to prescribe the set of thresholds a priori. We'd like to be able to come up with an adaptive scheme, some ideas in the pipeline, but any other ideas would be welcome. We want to look at the idea of how we choose the taus for the different levels. And so far we were using the same discrepancy metric for both low fidelity and high fidelity. And that doesn't necessarily give you the best ROC characteristics. So we could potentially do different acceptance reject criteria, depending on what simulation we're dealing with, to give better predictive performance. And then we can do different types of models. To summarize, we've generalized this multi-fidelity approach to other likelihood-free methods. By combining this with multi-level, we can do multi-fidelity ABC with multi-level for variance reduction. And then we get, nice speed ups, basically, 2 orders of magnitude for the examples we're looking at. And I've seen that in other examples. And yeah, that's all I have to say. I'll finish there. And here's some preprints. So questions about preprint 1, I recommend direct them to Tom. And questions to do with preprint 2, you can hassle me about them. So yeah, the first section talking about this preprint, the second was this one. Thank you for your time.
Thanks a lot, David. Very, very interesting. So I applaud you and on behalf of the audience, and I open the floor, but I'll stop recording